In this video, we'll be discussing the idea of force of gravity and how it affects objects. Gravity is a non-contact force, meaning that it has a noticeable effect even when the objects are separated. It is produced by any objects with mass, and it attracts other bodies of mass towards the center of it. In our case, we'll be mostly dealing with the gravitational field of the Earth, pulling us towards the center of the Earth. So what is the size of this force? Is it the same for all objects? Or does it vary based on object mass? We can find this with a simple experiment using a 10 Newton spring scale, a variety of different size masses, and some gravity. Before we start anything, we need to create our data table, with one column for independent variables, the mass of the objects in kilograms starting at 0 and going up by 0.05 kilograms, and the second column for our dependent variable, the force of gravity in newtons. So how can we measure the force of gravity with a spring scale? When we hang a mass on a spring scale, it gives us a reading in newtons, which indicates the amount of tension force felt by the spring. And since the mass isn't accelerating in the y direction, we can conclude the net force in the y direction is balanced, and thus the tension force is equal to the force of gravity. Now let's begin the experiment. The results for the experiment should be around these values. First, we have no mass, which has a force of 0 newtons. Next is the 0.05 kilogram mass, which has a force of approximately 0.5 newtons. The 0.1 kilogram mass shows a force of approximately 1 newton. The 0.15 kilogram mass shows a force of approximately 1.5 newtons. The 0.2 kilogram mass shows a force of approximately 2 newtons. The 0.25 kilogram mass shows a force of approximately 2.5 newtons. The 0.3 kilogram mass shows a force of approximately 3 newtons. The 0.35 kilogram mass shows a force of approximately 3.5 newtons. The 0.4 kilogram mass shows a force of approximately 4 newtons. The 0.4 kilogram mass shows a force of approximately 4.5 newtons. The 0.5 kilogram mass shows a force of approximately 5 newtons. Now that we have our data table, let's graph this. On the x-axis, we will put the independent variable, the mass of the mass in kilograms, and on the y-axis, we will put the dependent variable, the force of gravity on the object in newtons. We'll plot the different data points and connect it with a line of best fit. And we see that the graph shows a linear trend indicating a direct relation between the mass of the object and the force of gravity experienced by the object. And this relationship, known as the gravitational field strength, can be obtained by finding the slope of the trend line. So now, let us try and find the gravitational field strength of Earth. To find the slope, we find 2 points on the trend line, points 0.5, 5, and 0, 0. With the equation m equals to y2 minus y1 divided by x2 minus x1, we can see the slope and the gravitational field strength of the Earth, according to our experiment, is 10 newtons per kilogram. Now the more accurate gravitational field strength of Earth that we'll be using for class is actually 9.8 newtons per kilogram, which is very close to the results we obtained from our simple experiment. Now, with this value, we can create an equation that relates the force of gravity to the mass on Earth. An equation very similar to the equation of our graph. Fg equals to 9.8 times mass. Lastly, let's do a sample problem. How much does a car weigh on Earth if it has a mass of 9,000 kilograms? We have the given mass, which is 9,000 kilograms, and we are asked to find the weight of the car. Weight in physics is different than how we would use it in our everyday conversation. It simply refers to the gravitational force experienced by the object in newtons. So to solve this, we just substitute it into the equation, and we would get 88,200 newtons of force. So the car experiences 88,200 newtons of force, and thus has a weight of 88,200 newtons on Earth.